You've used them your entire life without thinking about them for a single second. A tiny wooden stick with a colored tip. You drag it across a rough strip of cardboard and fire appears in your hand. But that moment, that fraction of a second between friction and flame, is the result of a precisely engineered chemical chain reaction that took human civilization over 1,000 years to figure out how to control. And it begins long before the factory. It begins with a log. The preferred wood is aspen, poplar, or pine, softwoods selected not by accident, but by design. They burn smoothly and consistently. They do not produce excessive smoke. They do not leave behind a glowing ember after the flame goes out. At the sawmill, those logs are debarked and sliced into thin veneer sheets, which are then fed through chopping machines that cut them into uniform rectangular splints, thin, precise, identical. Each one cut to an exact length, an exact cross-section. These are the raw sticks that will eventually become matchsticks, though at this stage, they're nothing more than pale slivers of wood moving through a machine in their thousands. At the match factory, the loose splints are sieved over perforated plates. Anything undersized, anything malformed is removed. The usable splints are then slotted into the holes of long perforated aluminum belts arranged in a grid, each splint standing upright with one end protruding, ready to receive what comes next. Before anything is applied to the tip, the wood itself has to be prepared. And this is the part that most people never consider, because the treatments applied at this stage are invisible in the finished product. But without them, the match simply does not function safely. The splints travel on their aluminum belts through a bath of ammonium phosphate solution. The purpose of this is specific. It prevents the wood from afterglowing. A match that continues to smolder after you blow it out is a fire hazard. The ammonium phosphate eliminates that risk at the source, deep in the fibers of the wood, before a single drop of chemistry has touched the tip. After this bath, the splints are dried. Then they move through a second treatment, molten paraffin wax. The wax serves a different function entirely. It bridges the moment between the head catching fire and the wood itself beginning to burn reliably, giving the flame somewhere to travel in those critical fractions of a second after ignition. Without it, the reaction from the head may not transfer cleanly to the splint. After the wax, the splints are dried again. 2 baths, 2 drying stages before the head compound has even been mixed. Now the chemistry arrives, and this is where the precision becomes extraordinary. To understand what happens next, you first need to understand what a safety match actually is, because a safety match is not a single chemical system. It is 2 separate chemical systems deliberately split apart that can only react when brought together through friction. Neither half can ignite on its own. The match head and the striking surface on the side of the box are designed to be useless without each other. The match head contains potassium chlorate, the oxidizing agent, the chemical that supplies oxygen for combustion. Combined with it are sulfur and antimony sulfide as fuel, along with silica to control the rate of combustion, stabilizers, binders, and coloring agents. The striking surface on the side of the box contains red phosphorus, powdered glass to generate friction, carbon black, a neutralizer, and a gelatin binder. When the match head is dragged across the surface, the friction produces heat. The heat converts a trace of red phosphorus into white phosphorus. The white phosphorus reacts instantly with the potassium chlorate in the match head, producing a burst of heat that ignites the antimony sulfide and sulfur, which ignite the wood. The entire chain reaction takes less than 1 second. This 2-part system exists because of a catastrophe. The earliest friction matches used white phosphorus directly in the match head, a single unified system. They worked, but white phosphorus is extraordinarily toxic. Factory workers who made them in the 19th century developed a condition called phossy jaw, in which the jawbone would begin to glow faintly green in the dark before the bone itself began to rot away. It took decades of industrial pressure and eventual legislation to replace white phosphorus entirely. The red phosphorus system, split between head and box, was the solution. Safer to manufacture, safer to store, and controllable in a way that white phosphorus never was. Back on the factory floor in an industrial blender, the head compound is being prepared. Gelatin is combined with hot water and potassium chlorate powder, along with the sulfur, the antimony sulfide, the silica, the binders, and the coloring agents. The result is a thick paste, a liquid with a precise chemical composition that has been arrived at through decades of refinement. The splints, still standing on their grid formation on the aluminum belts, are conveyed to the dipping stage. The protruding tips are lowered into the compound. The depth of the dip, the viscosity of the paste, the speed of the machinery, all of it is controlled. Too thin a coating and the match will not ignite reliably. Too thick and the head will crumble or burn unevenly. The machinery applies the same coating to every single match on the grid. One pass, uniform across thousands of splints simultaneously. Once coated, the heads move under hot air blowers or infrared lamps. The heat solidifies the chemical coating and bonds it to the wood. And here, the environment itself becomes part of the process. Factories handling potassium chlorate, sulfur, and phosphorus compounds at scale maintain strictly controlled temperature and humidity throughout. Because in an environment like this, a single uncontrolled ignition event does not stay small. While the matches are being produced, the matchbox is being manufactured separately, and it is as precisely engineered as the matches it contains. The striking surface applied to the side panel is not sandpaper. It is a formulated chemical coating: red phosphorus, powdered glass, carbon black, a neutralizer, and a gelatin binder mixed into a paste and applied to the cardboard. The formula is carefully controlled. Enough red phosphorus to initiate ignition reliably through friction. Not so much that the box risks self-ignition during shipping or storage. Every matchbox you've ever held has been quietly calibrated to that balance. Before any match leaves the factory, the batch is tested. Sample matches are struck and must ignite on the first attempt within a defined number of strokes. Burn time is measured. The structural integrity of the head is checked. Anything that crumbles, anything that fails to ignite, anything that burns outside the acceptable range is pulled from the line. The raw materials are recycled back into the process and the testing continues. The finished matches are removed from the aluminum belts, counted, and inserted into the boxes. The boxes are sealed, packaged into cartons, and sent out to a distribution chain that will eventually place them on a shelf somewhere in the world, where a hand will reach out and take one without giving it a single thought. Billions of matches are manufactured every year. India is among the world's largest producers, with hundreds of factories operating across the country. Sweden, once the global center of match manufacturing and home to the innovations that made the modern safety match possible, gave the world many of the principles that still govern the process today. Every time you strike a match, you're triggering a chemical chain reaction that took human civilizations over 1,000 years to engineer into something small enough to fit in your pocket and safe enough to hand to a child. The wood chosen for its burning properties, the ammonium phosphate to prevent an afterglow, the paraffin wax to carry the flame, the potassium chlorate and the red phosphorus kept deliberately apart, until the moment of your choosing. The powdered glass, the gelatin, the controlled dip, the precise drying temperature, the carefully calibrated striking surface. Every single element exists because without it, the reaction either fails entirely or cannot be controlled. Fire in your hand in under a second. Nothing about it is simple. If that changed the way you think about something you've handled your entire life, subscribe, because that is what we do here.